Today I'll tell you how to stumble upon the solution to the swine in a line puzzle. I have to make a confession. I've never really solved this puzzle myself. I reverse engineered the rules of the game from knowing what the winning strategy was going to be. More specifically, starting from what I knew about the theory of abelian sand piles, which I'll talk about a little bit in the next video, I knew what I wanted the set of winning positions in this game to be, and I knew what kind of moves were allowed, and I worked my way backwards from there, trying to make the rules as simple as possible, and then dressing it up with pigs to make it fun. So I was really eager to see how people actually solved this puzzle when they didn't know the answer in advance. Some people solved the puzzle by letting their computers do all the work. That's a good approach, but the lessons we learn from such a solution are about how to write good code, not how to think about puzzles. One way some people solved the puzzle was to look at positions near the end game, where the board is nearly full. It's especially good to focus on the case where there are two empty pens and every other pen has one pig in it. Ignore these green letters for now. For instance, say the two empty pens are pen 3 and pen 4. If you experiment a bit, you'll find that the only winning move is to put a pig into pen 7. On the other hand, if the two empty pens are pen 3 and pen 5, the only winning move is to put a peg into pen 8. Or if the empty pens are pen 3 and pen 9, the only winning move is to put a pig into pen 2. By doing enough detailed analyses of endgames and by tabulating the results, you're likely to notice that the winning move is the sum of the locations of the empty pens, or rather, the last digit of that sum, unless that last digit is 0, in which case you're sunk. Incidentally, one feature of the winning strategy is that when you have the advantage and you're implacably following a winning line, your moves will symmetrically mirror your opponent's. When your opponent puts a pig in pen k for some k, your response is to put a pig in pen 10 minus k. It's a good idea to keep your opponent from noticing that you're doing this, but when you start from an empty board, your opponent is bound to notice what's going on. One broadly useful problem-solving strategy is to replace a problem by a similar but simpler problem. Instead of 9 pigs and 9 pens, use 3 pigs and 3 pens. Then you get a game that you can analyze completely by hand. If you're lucky, you find a pattern that applies to the original problem. I don't know if anyone used that method for swine in a line, but they could have. The general rule for winning the game when there are n pigs and n pens turns out to be, after your opponent has finished with all the consequences of her move, add up the positions of the empty pens and divide that sum by n plus 1. If the remainder is 0, you're out of luck. But if the remainder is bigger than 0, then that tells you what pen to put a pig into. There's a more abstract approach to solving the puzzle, which I'll mention because it's typical of the philosophy of problem solving that mathematicians often adopt in their research. You might have noticed that near the end of the game, adding a pig to any already occupied pen tends to lead to a long chain reaction. A novice problem solver notices this and finds it discouraging. An experienced problem solver notices it too, but then thinks, there's got to be some order to this chaos. There's got to be stability amid the apparent change. When there are two pigs in the same pen, and one goes left and one goes right, what doesn't change? At this point, a physicist might tap the mathematician on the shoulder and say, the center of mass of the pigs in the pens doesn't change. That is, the average of the locations of the pigs in the pens is unaltered. The average is the sum of the locations of the pigs divided by the number of pigs. So one might conclude that the sum of the locations of the pigs in the pens is what doesn't change when one pig goes left and the other goes right. Even without physical intuition as a guide, someone with experience in mathematical problem solving, having seen the idea of place value show its worth in many settings, might have the idea of using some sort of place value scheme to assign a value to positions. Not knowing ahead of time how much value to assign to the respective pens, a mathematician might temporarily treat them as unknowns. Say, pen 4 has value x, pen 5 has value y, and pen 6 has value z. So, for instance, if there were pigs in just those 3 pens, the total value of that position would be x plus y plus z. But how should we choose x, y, and z? The total place value of a position is supposed to remain unchanged when we trade 2 pigs in pen 5 for a pig in pen 4 and a pig in pen 6, left, right, which translates into the constraint that y plus y should equal x plus z. You can massage this into the equation y minus x equals z minus y, and that makes sense. If we want the total value before and the total value after to be equal, then y minus x, the amount of value the first pig loses when it goes from 5 to 4, must equal z minus y, the amount of value the second pig gains when it goes from pen 5 to pen 6. Anyway, we find that the numbers x, y, and z, pillars of the strange place value system we're in the midst of designing must form an arithmetic progression of length 3. The same reasoning shows that the values of all the pens from left to right, not just pens 4, 5, and 6, must be an arithmetic progression. If we're going to have a place value scheme in which the total value of the pigs doesn't change when a player carries out the consequences of a move, then it becomes natural for us to try letting the arithmetic progression be the numbers 1 through 9. Of course, in the process of designing this customized place value system, we realize sooner or later that there's trouble at the ends of the line. We notice that the place value of the pigs can't really be unchanged by all the possible consequences of a move. When pigs go back into the field, the total value of the pigs may change. It would be possible at this point to abandon the whole place value idea, but a little persistence reveals the trick of focusing not on the total value, but only on its last digit. That illustrates an important principle of problem solving. When an approach doesn't seem to work, don't scrap it entirely. See if you can find parts of the approach that do work. I'll end this video with a challenge for you. Can you come up with some sort of place value system that will help you analyze the one left, one out version of swine in a line? I'll remind you that in this variant, the consequence of having two pigs in a pen is that one pig moves to the left and the other pig moves back into the field. For full details, watch the third video in this series. Can you come up with a version of place value that unlocks the secrets of this game?